Hello, I'm Travis Van Bradford, and as you can see, this video and audio is of a much higher quality, and that is because I am recording this on the Samsung Galaxy S21, and the microphone is from Amazon, and it is from a company called Maybesta. Before I delve into the topic of this video, I highly infer that viewership and engagement has gone down since 2016 because of the quality of the video and the quality of the audio hasn't really been up to standard. That does matter. Uh, Back in 2016, when it comes to that Boltzmann brain video, and I think it was a video on dark flow and certain things attracting things outside the cosmological horizon, my brother recorded that video. And now he is super duper famous. His name is This Is Corey. He's on TikTok. He has almost 1 million followers, if not 1 million followers. And he has to focus on that now. Not to say that we still don't collaborate, we do. But now my wife is helping me record this video, and we have a lot of interesting settings. So now this channel will shift into another eon. With that being said, there are two types of videos that are the most popular on this channel. Unfortunately, the most popular are things on a sociological order of magnitude, by which things are perceived based on people's mood, circumstances, and relationships with other humans. But the second most deal with existential topics, or at least people masquerading self-preservation as empiricism. So let me delve into that a little bit more. Some of my most popular videos are on the Boltzmann brain and the Poincaré recurrence. The Boltzmann brain is this notion that after our universe reaches its final energy state, 10 to the 10 to the 10 to the whatever years from now, there will be these Boltzmann brains that arise out of some type of thermal or quantum fluctuations, or the universe will start over due to uh, the particles or certain aspects of Kolmogorov complexity inducing some kind of Poincaré recurrence where the arrangement of these particles or quantum state of the universe is put back in a state that it was in before to a state to where it's very similar to this very moment that I'm making this video. Now, both of those have been somewhat debunked, and they are both on methodologically and empirically shaky grounding. With Sean Carroll has written a paper on why Boltzmann brains are bad. With the Poincaré reoccurrence, it's a little bit more shaky. But the second law of thermodynamics and certain laws of thermodynamics may make it where certain things cannot start over in exact configurations with 10 to the 97 particles in the observable universe. And that's not even including things outside the cosmological horizon. However, this video is going to be about us taking our fate into our own hands, or at least analyzing the feasibility to do as such. Now, I'm going to start off with something very existential. And then I'm going to analyze the feasibility of us circumventing this. Now, first, I'm going to get into the heat death of the multiverse. Now, before I get into that, we got to analyze the empirical and theoretical feasibility of the heat death in and of itself and the existence of a multiverse. Now, it is quite clear that there will probably be a heat death of this universe just due to dark energy and possibly proton decay, but that hasn't been proven yet due to certain things that we have to do when it comes to neutrino oscillations and W and Z bosons and things in the weak nuclear force regime. However, it is clear based off of our current findings with type 1a supernova and the cosmic microwave background that the universe is expanding at an accelerating rate and heat death will probably occur. As for the existence of a multiverse, a lot of people are very much against it. Sabine Hossenfelder is against it, whereas people like Andre Linde and Alan Guth have stated that such a thing could exist due to cosmic inflation, which solves certain things dealing with the flatness and horizon problems in our cosmological research. Do I infer if the multiverse is real or not? There's surely something beyond the cosmological horizon, but we have no way at this time of detecting what it is. But to say that there's nothing beyond the cosmological horizon, that would be quite foolish. So let's just entertain the notion of a heat death of a multiverse. The ultimate fate of the multiverse is a topic of profound significance and complexity. According to Japanese physicist Yasunori Nomura of UC Berkeley, the journey begins from a generic, eternally inflating state where the coefficients of any components in an unstable vacuum will inevitably decay. In the intricate string landscape, and this is assuming that string theory is feasible, this decay process implies that all de-Sitter and non-supersymmetric Minkowski vacua will eventually transition into a lower energy vacuum due to the vast number of possible decay channels. As a result, the multiverse state will asymptotically transform into a superposition of supersymmetric Minkowski and singularity states associated with black holes and big crunch singularities. Now, let me pause. The big crunch is this notion that if dark energy were to somehow run out, or if gravity was to overcome dark energy, the universe would eventually contract back into itself. We don't have any data based off of the Planck Space Observatory, WMAP, COBE, or the James Webb Telescope, or the Hubble Space Telescope that that's going to happen. It's clear that that dark matter is causing the universe to accelerate in expansion. Nevertheless, supersymmetric Minkowski states refer to configurations within a bubble universe on a supersymmetric Minkowski vacuum. So let me get into these vacuous states. The Casimir pole de force is this experiment in which there are two plates and a vacuum, meaning there's no air, no particles in this experiment, yet they can still attract each other. That shows that there is some type of metastable vacua in which even without any particles in this experiment, there are still quantum fluctuations. So there's vacuous states or quantum vacuous states that are lower than ours, and this can affect how the Big Bang and how the universe or even other universes could arise. But this universe on a supersymmetric Minkowski vacua, which asymptotically approaches these vacuum states, can happen as the universe expands. And this phenomenon is a direct consequence of the second law of thermodynamics, as the Hilbert space dimensions of Minkowski and singularity worlds are deemed as infinite. Now, can this be circumvented, this whole heat death of the multiverse? Could we get to a point to where we could surpass our current spatial, temporal, and cognitive limitations and get to a point to where this could be circumvented after eons and eons and 10 to the 10 to the 10 to the 10 to the 56 or 10 to the 10 to the 10 to the 10 to the 120 years from now? And we're going to analyze that, the feasibility of that. Now, according to physicist Jorma Garriga, Mukhanov, and he's a Russian cosmologist, and Kendi Olum, and the great Alexander Vilenkin, they had a paper in 1999 titled eternal inflation, black holes, and the future of civilization. If our optimized descendants can figure out how to navigate quantum inequalities, according to this paper, and learn to generate negative energy in a sufficiently large volume, it might be possible to send a device with the purpose of recreating an approximation of our original universe to another universe after this particular one within the entire multiverse state, or possible multiverse state, if there is such a thing, succumbs to heat death. Inflationary cosmology explores the large-scale structure of the universe and its implications for long-term future civilizations. Cosmologists and physicists have discussed this in papers like this one I found on arXiv. Now, while each civilization is, at this point in time, ultimately doomed, it might still be possible to transmit accumulated knowledge to future civilizations. If the cosmological constant is positive, and at this point, due to dark energy, we infer that it is, and eventually dominates the universe, bubbles of the inflationary phase could start forming at a constant rate. According to MIT physicist Alan Guth, thermalized regions within these inflating bubbles could give rise to new galaxies, to new big bangs, and to new civilizations. In principle, it's possible to send a message or device to one of these regions, and perhaps even one aimed at recreating certain aspects of our current civilization, with the more hedonistic and degenerate aspects possibly either deleted or sent to these future entities to know what not to do. However, such a message or device would likely be intercepted by black holes. And I could get into a whole separate conversation about black hole singularities, whether singularities exist, black hole firewalls, Unruh radiation, Hawking radiation, entangled qubits in Hawking radiation. But it's clear that there would be a demarcation between our universe and whatever other possible universe there may be due to some type of black hole singularity. And this message or device would be likely intercepted by black holes, which nucleate faster than the rate of cosmic inflation, causing new universes to exist. And this is according to certain models in cosmic inflation. The formation of new inflating regions in our overall omniverse can also be triggered by gravitational collapse, but the probability is very low for that according to particular models. And this is requiring an enormous number of attempts for one outcome for this so-called device to be sent to another universe. The probability can increase if the energy scale of inflation is closer to the Planck scale, but this imposes limits on the amount of information that can be transmitted. Attempting to avoid quantum tunneling, and quantum tunneling is this notion that certain quantum phenomenon or particles or forces can surmount certain barriers that classical phenomenon or classical materials cannot. So to attempt to avoid quantum tunneling altogether would require violating quantum inequalities, which constrain the magnitude of negative energy densities. Creating new inflating regions without quantum tunneling would necessitate a violation of the weak energy condition, conflicting with quantum inequality. However, the limits of validity of quantum inequalities are not clear, and future research may show that the required violation is possible, offering some so-called hope or the desire for a certain outcome for future civilizations. Now, I've gotten into this earlier about the Casimir energy density and the electromagnetic vacuum between two conducting plates, but according to certain theories, this appears to be negative and permanent, which certain physicists infer that this violates certain equations. This negative energy density could be understood in terms of the quantum expectation value. With quantum fluctuations occasionally providing the required negative energy in a sufficiently large region, this makes this possibility of this device being sent to another universe makes the probability a little bit higher. Now, the quantum effects observed at high curvature, and this is getting into something that I particularly find interesting, is like uh, quantum effects on like the curvature tensor of the Einstein field equations or the stress energy tensor. These are things that deal with quantum gravity. But quantum effects at high curvature could significantly alter the dynamics of the gravitational field, assuming that there is a metastable state of limiting curvature that decays, releasing energy into particles. This leads into the formation of thermalized regions and the typical scenario of internal inflation inside black holes. During gravitational collapse, the effective energy momentum tensor in this particular model should develop negative energy densities that violate quantum inequalities. But we need to use something called adversarial modeling. And we need to try to understand the feasibility of everything I just stated. I'm not here to state that it's 100% possible to violate uh, certain things dealing with the weak energy condition and things like that. I'm merely analyzing the feasibility of it so that we can understand our limitations in our theories and models and hypotheses so that we could possibly surpass them. So when I cross-reference this information to figure out any kind of counter arguments, I ran into this paper from L.H. Ford and Thomas A. Roman from 1994 named The Average Energy Conditions and Quantum Inequalities. And they impose stringent limits on the magnitude and duration of negative energy densities. These constraints defined by the quantum inequality formula, where tau is the sampling time and T is the energy density, are firmly rooted in quantum field theory, ensuring stability and consistency within the framework of known physics. This inequality sets a bound on the amount of negative energy that can be observed over a given time interval. As of me uploading this video, there is no experimental evidence supporting the existence of stable macroscopic regions of negative energy. There may be microscopic regions based off of quantum fluctuations in those plates in the Casimir polar force that I mentioned earlier, but there is no experimental evidence for macroscopic regions of negative energy. Now, observations of negative energy, as I talked about earlier, seen in the Casimir polar force, are very minuscule and transient. And these amounts do not scale up to larger volumes. Theoretical models predict that attempts to sustain large volumes of negative energy would likely lead to violations of fundamental principles like causality and energy conservation. For instance, maintaining negative energy for extended periods could potentially result in closed time-like curves, which are solutions to Einstein's equations that allow for time travel. Hence, this would violate causality. Additionally, energy conservation would be violated, and this is expressed through a breakdown of the stress energy tensor in Einstein field equations in general relativity. Inflationary cosmology suggests that certain bubbles of an inflationary phase could form new galaxies and civilizations. So this has a bit more of a theoretical and slightly more empirical grounding. However, sending messages or devices to these regions would be very daunting. While the theory of inflation predicts the formation of these new regions, um, it would be extremely complex sending this device to these new regions. The exponential expansion described by the de Sitter space metric creates a vast distance between these bubbles. Current inflationary models, such as slow roll inflation models, characterize by the potential V, phi, and slow roll parameters that suggest that the formation of new inflationary bubbles even exists would be a rare event. The stochastic nature of bubble nucleation, as described by the Coleman-DeLucia instaton, and the vast separation between these bubbles make targeted transmission of these devices and the transformation of information extremely unlikely based off of current empirical and inferential models. Even if a message or device could theoretically survive the journey, the technological and energy requirements to encode, send, and decode such information, possibly involving Planck scale physics that requires things that deal with string theory, loop quantum gravity, grand unified theories, Patty-Salam models, Georgi Glashow models, Chern-Simons models, and Yang-Mills models combined are beyond our current understanding and capabilities. Moreover, the survival of such information in extreme conditions is highly speculative. The idea that these devices would be intercepted by black holes, which form at a faster rate than the inflating bubbles creating new universes, and that avoiding quantum tunneling would require, as they said earlier, violating quantum inequalities, which is fraught with practical challenges. Observations confirm that black hole formation is a common endpoint for massive stellar objects having some type of gravitational collapse and having regions of high energy density. The density and frequency of black holes in our universe present a formidable barrier to this hypothetical travel of these and the transmission of these devices. The probabilities involved in avoiding black holes while targeting specific regions of space that emerge out of inflating bubbles from cosmic inflation is at this time astronomically low. But that's why we're making this video, so we can understand the feasibility of this, so we could possibly surpass these limitations. Theoretical models suggest that quantum effects at high curvature could alter gravitational dynamics, leading to new thermalized regions and internal inflation inside black holes. And these effects are described by the semi-classical Einstein equations, in which they include particular quantum corrections. The renormalization group equations and the running of certain coupling constants at high energy scales, along with the Hawking radiation I was talking about earlier, contribute to our understanding of these dynamics. However, there is no direct experimental evidence supporting the idea that quantum effects at high curvature scales can lead to stable, large-scale inflationary regions. We only have theoretical evidence for such things. Our understanding of quantum gravity, encapsulated by frameworks such as what I mentioned earlier, string theory and loop quantum gravity, are still incomplete, and ongoing research is required to explore these possibilities. Given our current research, relying on such speculative mechanisms introduces significant uncertainty parameters to understand the feasibility of sending another message, or even ourselves, to a different universe. The formation of thermalized regions in internal inflation inside black holes remains a very theoretical construct without a lot of empirical validation. The proposition that creating new inflating regions without quantum tunneling would necessitate a violation of the weak energy condition and quantum inequalities, and this is met with significant theoretical resistance at this time. The weak energy condition states that for any time-like vector, quantum inequalities are fundamental to maintaining consistency in our physical theories at this time. Attempts to violate these conditions leads to paradoxes and inconsistencies within our theoretical framework. These conditions are essential for maintaining causality and stability for the space-time continuum. For example, violating the weak energy condition could result in exotic phenomena such as transversable wormholes, which are possible within the framework of general relativity, but they have not been observed. Future research may explore these boundaries of these conditions, but any proposed violations must undergo rigorous empirical testing. Until then, the assumption that these conditions can be violated remains speculative and unsupported by current empirical evidence. However, methodologically, we can use other non-anthropocentric methods based on inferences or other methodologies that could explore things beyond empiricism without getting into our mood, circumstances, relationships with other beings, or immaterial and non-physical phenomenon. Now, the Casimir effect demonstrates negative energy densities, which could occasionally provide the required negative energy in large regions. However, as I said earlier, the Casimir effect quantified by the force per unit area, where A is the separation between those plates I named earlier, is only observed on microscopic scales, as I said earlier. And the Casimir effect is observed between closely spaced plates at very small scales. They haven't really done this experiment with quantum fluctuations on a large scale. Extrapolating this effect to large volumes involves numerous assumptions and untested hypotheses at this time. And while it's intriguing, the Casimir effect does not provide a practical mechanism for generating large-scale negative energy required for the proposed scenario of sending or transmitting information from a device to another universe that is occurring due to, which is still somewhat theoretical, cosmic inflation. Theoretical extensions such as involving the dynamical Casimir effect need substantial empirical support to be considered viable. So I say all that to say this. If we are to take control of our own existence, the methodology by which we do this is going to have to go beyond faith. And it's going to have to go beyond hope. It's going to require a certain amount of adversarial modeling in which we propose a hypothesis and rip it apart with counter arguments and analyze the weaknesses so that we can eventually surpass them.